Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Today we are going to discuss new topic in chemical equilibrium, that is Lee-Chatter's principle, which is nothing but external factors affecting equilibrium constant. So this is very important topic. Lee-Chatter's principle. Applications of Lee-Chatter's principle is most important for the entrance exams. So we are going to continue this topic and we are going to finish this topic in this lecture. So please listen carefully. Now we'll start. Lee-Chatter's principle. So external factors affecting equilibrium, that is Lee-Chatter's principle. What is Lee-Chatter's principle? Let us discuss now. If a change is applied to a system at equilibrium, suppose a reaction is there at equilibrium, then if it is subjected to change, then the equilibrium will be shifted in such a direction in which it can minimize the effect of change applied and the equilibrium is established again under new conditions. This is called Lee-Chatter's principle. So if a change is subjected, if a system is at equilibrium, so once again I repeat the statement. For a system at equilibrium, if it is subjected to change, the equilibrium will shift in such a direction to nullify the change. It will nullify the change. Nullify the change means it will try to nullify. Nullify means zero change. So again, bringing back, it is try to nullify the change. Nullify change. So that is, if a change is applied to the system at equilibrium, then equilibrium will be shifted in such a direction in which it can minimize the effect of change applied and the equilibrium is established again under new conditions. So this is called Lee-Chatter's principle. So what is Lee-Chatter's principle once again? For a system at equilibrium, if it is subjected to change, then the equilibrium will shift in such a direction where it nullifies the change. It nullifies the change. So that is called Lee-Chatter's principle. So now we'll see application of Lee-Chatter's principle. So how can we change a system? By the effect of concentration, temperature, and pressure, and volume. So if the concentration of a component is increased, either the reactant or product, if a concentration of a component is increased, the reaction shifts in the direction which tends to decrease its concentration, So in the following example, nitrogen and hydrogen combines to form ammonia. If the concentration of nitrogen or hydrogen, that is reactant, is increased at equilibrium, then the equilibrium will shift in the forward direction where there is less number of concentration. Automatically, if you increase the concentration of nitrogen and hydrogen, where the equilibrium will shift towards right hand side. That is where there is less, tends to decrease its concentration. So if the reactant's concentration is more, automatically product's concentration is less. So the reaction will shift towards products, that is forward reaction. As the reaction is shifting towards products, it is nothing but forward direction. So if the concentration of reactant is increased at equilibrium, then reaction will shift in such a direction where the change is nullified. So in this case, the reaction will shift in the forward direction because in the products there is decrease in number of moles. Similarly, if the concentration of product is increased, then reaction shifts in backward direction. This is very important. The applications of Lee-Chatter's principle is very important. They'll ask in the entrance exam. So first concept, that is concentration. If the concentration of a component is increased, the reaction will shift in a direction which tends to decrease its concentration. And finally, it will come to equilibrium back. So the addition of any solid component does not affect the equilibrium. Very important. The addition of solid component does not affect the equilibrium because, as we already know, the concentration of solid is taken as unity. As the concentration of solid is taken as unity. So concentration of solid is taken as unity. So that's why the effect, if the in the reactants, if in this reaction all are gases, so it will affect. But if the reactant is, our product is solid in nature, by the addition of the reactant, even though by the addition of more amount of reactant also, the equilibrium will not shift because the concentration of solid is taken as unity. So this is called effect of concentration. If the concentration of a component is increased, reaction shifts in a direction which tends to decrease its concentration. Next, continuation. Effect of volume. So effect of volume is based on pressure. So if volume is increased, pressure decreases. From Boyle's law, we know this. Hence, reaction will shift in the direction in which the pressure increases. That is, in the direction in which the number of moles of gases increases, because PV is equal to nRT, since pressure is proportional to number of moles. Pressure and volume are proportional to number of moles. We can say the pressure in which the pressure increases, that is in the direction in which the number of moles of gases increases, and vice versa. So if volume is increased, then we can say delta N is greater than zero. For that reaction, if delta N, what is delta N of G? Where delta N is equal to number of moles of products minus number of moles of reactants, gaseous products and gaseous reactants. So delta Ng is greater than zero. Reaction will shift in the forward direction if the volume is increased. See this condition, very, very important. If the volume is increased and for that reaction delta N is greater than zero, then we can say the equilibrium will shift in the forward direction. And if volume is increased and the delta N for the reaction is zero, that is in the previous case, then the reaction will shift in the backward direction. Please remember these two statements, these three statements, very, very important. And if there is no effect of delta N, then the reaction will not shift, because as delta N becomes zero, so if you even the volume is increased for a reaction for delta N zero, there is no effect of equilibrium. That is for this reaction, if you see here, hydrogen 1 mole, iodine 1 mole to form 2 moles of hydrogen, no effect of volume. Even if you increase the volume of hydrogen, or you increase the volume of iodine, or you increase the volume of hydrogen iodide, there is no effect of this reaction. There is no effect on the equilibrium. So this is the dependence of volume. If volume is increased, then for the reactions which have delta N greater than zero, the reaction will shift in forward direction. And the reactions which have delta N less than zero, the reaction will shift in backward direction. And for the reactions which have delta N is equal to zero, there is no effect of volume and pressure. There is no effect of volume and pressure. And for this reverse condition is delta pressure. So you can take effect of volume like this. Very, very important, effect of volume. Next continuation, we'll see effect of pressure now. So if delta N is greater than zero, example, you can see here, we have given examples also. PCl5 changes to PCl3 plus Cl2. In this case, what is the value of delta N? Delta N is equal to 2 minus 1, because 1 mole, that is products, minus 1, that is equal to 1. Since delta N is greater than 0, we can say if your volume increases, if the volume increases, the equilibrium will shift in forward direction. So now on increasing volume, QC decreases. What happens? What happens to volume? If you increase the volume, automatically QC decreases, because QC is proportional to 1 by V. So for delta N greater than 0, so on increasing volume, QC decreases. As now QC is less than KC, reaction will shift in forward direction. Thus, if volume increases, QC decreases, forward shift. If volume decreases, QC increases, backward shift. Very, very important point. Clearly, we have mentioned it. So please note down in your classwork. So if volume increases, QC decreases. That is, reaction quotient decreases. So that's why the equilibrium will shift forward direction. And if volume decreases, QC increases, because QC is proportional to 1 by V, as we already know. QC is equal to number of moles by volume of solution. Number of moles is N and volume of solution is V. Since Q is proportional to 1 by V, as V increases, Q decreases. As Q increases, V decreases. So if volume increases, QC decreases, automatically the equilibrium will shift in forward direction. And if volume decreases, QC increases. So the equilibrium will shift in backward direction, backward shift and forward shift. So this is very, very important. Please note down. Next, continuation. If delta N is less than zero, for example, for this reaction, nitrogen combines with hydrogen and forms ammonia. Now in this reaction, what happens to delta N? Delta N becomes negative. That is, delta N is equal to 2 minus 4, because 3 plus 1 is 4. So 2 minus 4 is equal to minus 2. Since delta N is equal to minus 2, it is less than 0. As volume increases, what happens? QC is proportional to V square. For delta N less than 0. As volume increases, QC increases, backward shift. and as volume decreases, QC decreases forward shift. So as volume increases, delta n is less than 0. As volume increases, backward shift. As volume decreases, forward shift. So that's why effect of volume is most important, since for delta n greater than 0, if volume increases, QC decreases. But for delta n less than 0, if volume increases, QC also increases, because this is the equation. Now you can see QC is equal to n number of moles of ammonia by V whole square by n number of moles of nitrogen by V whole into n number of moles of hydrogen by V whole cube. This is cube into 1, 4, and this is 2. So automatically Q is proportional to V square. Since volume increases, automatically Q also increases. That is reaction quotient also increases. Since volume decreases, QC also decreases for this case, which case that is delta N is less than 0. So if QC is greater than KC, forward direction. QC is greater than KC, we already know it is backward shift. And if QC is less than KC, there is backward reaction. And this is, if QC is less than KC, forward reaction. This already we have seen in the last lecture. So this is called QC and KC. So V is proportional. As V increases, QC also increases. As V decreases, QC also decreases. Hence, the equilibrium will shift backward shift in the first case, and the later case it is forward shift. Next continuation. Next, effect of pressure. So first we have done concentration, next volume. Third effect is effect of pressure. This is also very, very important. On increasing the pressure, equilibrium will shift in the direction in which the pressure decreases. That is, the number of moles in the reaction decreases and vice versa. Because pressure is proportional to number of moles, we can say pressure decreases, number of moles in the reaction also decreases. So P is proportional to number of moles. So for delta N is equal to 0, no effect. Number of moles, no effect. This we can say number of effects we cannot see. It is no effect. It is no effect. And for delta n greater than 0, QP is proportional to P. So if delta n is equal to 0, if you increase the pressure, the equilibrium will shift in forward direction. Equilibrium will shift in forward direction because QP is also proportional to P. QP is proportional to, because partial pressure of P into mole fraction of PCl3, uh, mole fraction of Cl2, mole fraction of PCl5 into total pressure. So this is nothing but total pressure into mole fraction. That is nothing but partial pressure, since P is proportional to number of moles. So on the whole, it's very simple. We can say if delta N is less than greater than 0, reaction will shift. QP also increases. As QP is greater than KC, we can say backward direction. For delta N is greater than 0, backward reaction takes place. Reverse direction or backward reaction, because QP increases. So QP is greater than KP. So automatically backward reaction takes place. Very, very important, this Le-Chatter's principle. For low pressure, QP also decreases, so forward shift. For high pressure, if you increase the pressure, QP also increases, backward shift, as I told you. So for if delta N is equal to 0, for the reaction delta N greater than 0, I'll write it here clearly. Increase of pressure, backward reaction, and decrease of pressure, forward reaction. Just opposite to volume. For delta N greater than 0 volume, if you take, what happens? Increase of volume, backward reaction, and decrease of volume, forward reaction. Next, for the reaction delta N less than 0, like ammonia, formation of ammonia, we can say QP is proportional to 1 by P square. By this, you can say if high pressure, increase of pressure, for this step, for delta N less than 0, you can note down this straight away. For delta N less than 0, for the reactions of type where delta N is less than 0, in this case, we know delta N is equal to -2. So increase of pressure, what will happen? QP decreases, forward shift. So it is but forward reaction. And decrease of pressure, backward reaction. Because in this reaction, QP is proportional to 1 by P square. Same thing for volume also. Increase of volume, forward reaction, backward reaction, decrease of volume, forward reaction. Just opposite to pressure, volume, because pressure is proportional to 1 by V. Since pressure is proportional to 1 by V, so this is taking place like this. So higher increase of pressure, QP decreases, forward shift. Decrease of pressure, QP increases, backward shift. So straight away I have written for the reactions where delta N is less than 0, increase of pressure, forward reaction, and decrease of pressure, backward reaction. For the reactions where delta N is greater than 0, increase of pressure, backward reaction, decrease of pressure, forward reaction. These conditions they'll definitely ask in the examination. So please note it down, very, very important. And if delta N is equal to 0, next one, no effect of pressure. As we already know, if delta N is equal to 0, no effect of pressure. Next, we have effect of temperature. This is also important. So total 4: temperature, pressure, volume, concentration, and number of moles also. So this is temperature, effect of temperature. For endothermic forward reactions, if temperature is increased, you have to temperature depending on endothermic or exothermic. So for endothermic reaction means where delta H is positive. Delta H is positive, that is called endothermic reactions. Endothermic reactions. So for endothermic forward reaction, if temperature is increased, equilibrium is increased, equilibrium moves in forward direction. For the endothermic reactions, as the temperature increases, forward reaction, that is reactants changes to products. Similarly, for exothermic reaction, forward reaction of temperature is increased, equilibrium moves in backward direction. It means for increase of temperature for exothermic reactions where delta H is equal to negative, where delta H is equal to negative, by the increase of temperature, equilibrium will shift backward reaction. That is nothing but products changes to reactants. So please note down these conditions. So for if the reaction is endothermic, we can say endothermic. How can we identify if delta H is positive or delta H is negative? If delta H is positive, we'll say it is endothermic reaction, or delta H is negative, we'll say it is exothermic reaction. And further, they give like this also. For example, A plus B gives rise to C plus D plus 19.8 kilojoules. It means this side it is plus means it is exothermic. Exothermic. Please note down this because this type of examples they will not give. So please note down. For the reaction, if they are given like this. Similarly, if they are given like this, A plus B gives rise to C plus D minus 20 kilojoules. We can say it is endothermic because if you shift this to this side, it will become plus. Plus means by gaining energy. So this is endothermic. Instead of giving delta H values, they'll give like this also for confusion. So if they are given confusion sake like this, A plus B gives H to C plus D plus 19.8 kilojoules. By increasing the temperature, what happens to the equilibrium? The equilibrium will shift since it is exothermic reaction. By increasing the temperature, the equilibrium will shift to backward reaction. That is, product changes to reactants. Product changes to reactants. Similarly, they're given A plus B gives H to C plus D minus 20 kilojoules. It means endothermic reaction. By increasing the temperature, what happens to the equilibrium? The equilibrium will shift in the forward direction. So please note down all these values, all these slides, very, very important. If you didn't understand also, listen 2-3 times, definitely you'll understand clearly. So for endothermic reaction, forward reaction, if temperature is increased, equilibrium is increased, so equilibrium moves in forward direction. So for exothermic forward reaction of temperature, if it's increased, equilibrium will move in backward direction. So these are the conditions. And if they are given delta H positive, we can say straight away endothermic reaction. If delta H is negative, we can say exothermic reaction. But instead of giving delta H and delta H values, if they are given for the reaction like this, that is A plus B gives H to C plus D, for example. So it is here, it is forming A combines with B to form C and D plus 19.8 kilojoules. It shows that it is exothermic because if you take plus, this side it will take minus. And if it is A plus B gives rise to C plus D minus 20 kilojoules, it is endothermic. So please note down here minus means endothermic, here plus means exothermic, and here plus means endothermic, and here minus means exothermic. So for delta H positive means endothermic, for delta H negative means exothermic. Whereas on the in the reaction, right hand side it is positive means exothermic, and left hand side, right hand side it is negative means endothermic. Simple it is. So please listen carefully. These things you have to understand. Then only you can apply the concept easily. Anyway, we are going to discuss at the end of this session so many questions. In that question, with that questions, I think 100% you will get concept easily. So please note it down. Next continuation. Effect of inert gas. Last effect is effect of inert gas. So inert gas at constant volume. If the reaction is at constant volume, if the equilibrium reaction is at constant volume, inert gas addition has no effect. Means, for example, you can say hydrogen combines with iodine to form hydrogen iodide. If this reaction is carried out at constant volume, suppose if this reaction is carried out at constant volume by the addition of inert gas like helium, neon, argon, any gas, inert gas, only inert gas at constant volume, by the addition of inert gas, there is no effect on equilibrium. For this reaction, there is no effect on equilibrium. Whereas at constant pressure, if inert gas is added to, then to maintain the pressure constant, volume increases. Hence, equilibrium will shift in the direction in which large number of moles of gas is formed. So, for the reaction delta n greater than zero, if by the addition of inert gas, volume increases. As the volume increases, reaction will shift in forward direction. For the reactions where delta n is less than zero, the reaction will shift in backward direction because by the addition of inert gas, volume increases. By the addition of inert gas, volume increases at constant pressure. So at constant pressure, by the addition of inert gas, we can say for by the addition of inert gas, if delta n is greater than zero, by the addition of inert gas, by the addition of inert gas that is what you can say in helium, helium, neon, argon, etc. to the equilibrium, equilibrium will shift to forward reaction. Forward reaction takes place. And delta n is less than zero, backward reaction takes place by the addition of inert gas. So this is very, very important point 1, 2, 3. And for delta n is equal to zero, no effect. Even though by the addition of inert gas, there is no effect on equilibrium. There is no effect on equilibrium. So this is called effect of inert gas addition at constant volume and at constant pressure. At constant pressure only it has effect. At constant pressure, what happens if the inert gas is added, then to maintain the pressure constant, volume increases. Hence, equilibrium will shift in the direction in which large number of moles is gas is formed. So that is, for the reaction delta n is greater than zero, large number of moles of gas is formed means it can be either reactant side or in product side, depends on the equation. So that's why that has been categorized like this. That is, if delta n is greater than zero for a chemical reaction, that is at equilibrium, we can say reaction will shift in a forward direction by the addition of inert gas. If delta n is less than zero, reaction will shift in the backward direction by the addition of inert gas. And if delta n is equal to zero for the reaction at equilibrium, by the addition of inert gas, it has no effect. It has no effect. So all these 3 points are very, very important. So finally, we have totally five factors depending on Lee-Chatter's principle. One is concentration, another is volume, third one is pressure, fourth one is temperature, and fifth one is inert gas. So total we have five. Based on these five concepts, we will be getting questions based on Lee-Chatter's principle in the entrance exam by the application of Lee-Chatter's principle. Let us see now application of Lee-Chatter's principle. So from Lee-Chatter's principle, by using all this, we can say we can predict the direction of reaction and we want to desired products also. What two changes on the equilibrium can keep it state undisturbed? What two changes on the equilibrium? So what are those two changes? You can just see here. Increase of temperature, since the reaction is exothermic. Since the reaction is exothermic, since delta H is negative, because they are given delta H value is negative, that is minus 92 kilojoules. So increase of temperature along with suitable increase of pressure. If you increase the temperature and with the increase of pressure along with suitable increase of temperature, by these two factors, if you increase the temperature, what happens to that reaction? As the reaction is exothermic, high temperature favors backward reaction. And if you increase the pressure, if you increase the pressure, since for this reaction delta N is less than 0, delta N is less than 0 because nitrogen delta N value is minus 2. Since delta N is less than 0, high pressure favors, increase of pressure favors forward reaction. So one way it is forward reaction, one way it is backward reaction. So automatically there is no change on the equilibrium. There is no change on the equilibrium. So this is the question. So increase of temperature along with suitable increase of pressure along with suitable increase of temperature. So two times it has come. So no need to take this. So increase of temperature along with suitable increase of pressure makes the equilibrium remains stable. Makes the equilibrium remain stable because as the reaction is endothermic exothermic reaction, because since delta H is negative, so high temperature favors backward reaction. And since delta N is less than 0 for this reaction, for the same reaction, we can say high pressure favors forward reaction. So by suitable values of temperature and pressure, we can make the equilibrium stable. We can make the equilibrium stable. So this is the answer. I hope it is clear. Next consideration, next question. 2N2O plus O2 gives rise to 4NO. Delta H is equal to 0. 2N2O plus 4O2 gives rise to, plus O2 gives rise to 2NO. All our gases here. Delta H is equal to 0. They have given delta H is 0. Means it is positive because for this reaction. What will be the effect on equilibrium when volume of the vessel increases? Since delta H is equal to 0, it is positive. So what will be the volume of the vessel? So for this, first we need to find for volume, we have to consider delta N values. What is the value of delta N? 4 minus 3. 4 minus 3 is equal to 1. That is, delta N is greater than 0. Since delta N is greater than 0 for this reaction, as the volume of the vessel increases, and what will be the effect on temperature as the temperature decreases? Since this is endothermic reaction, temperature decreases, backward reaction. Low temperature, backward reaction. And since delta N is greater than 0, volume increases, forward reaction. Volume increases, forward reaction. So by this you can say answer for this reaction is increasing volume of the vessel means decreasing pressure. As the volume increases, pressure decreases, since already we know. As forward reaction is accompanied by increasing the number of moles. Because since delta N is less than 0, greater than 0, as a forward reaction is accompanied by the increasing number of moles, decrease in pressure will favor forward reaction. So according to Lee-Chatter's principle. So if we increase the volume, automatically for delta N greater than 0, as volume increases, forward reaction takes place. As delta H is positive because it is 0, the reaction is endothermic. So decrease of pressure, temperature will favor the direction which is heat is released, that is backward direction. So if you decrease the temperature, what happens? Backward reaction takes place. As we discussed the same, here also we got the result. So if delta N is greater than 0, increasing volume favors forward reaction because decreasing pressure takes place. Next. So next, now question number 3. Now we are going to discuss. So as we have given less questions, so here I want to write important questions based on this. Now question number 3, based on these chapters. Question number 3, change in volume. Change in volume of the system. Change in volume of the system does not alter alter means change the number of moles, does not alter the number of moles in which of the following reaction, in which of the following equilibrium. This is the question. So option one, first option, nitrogen gas combines with oxygen gas to form nitric oxide. All are gases, gas, gas, and gas. Second option, PCl5 gives rise to PCl3 plus Cl2. This is also all are gases, gas, gas, and gas. Third option, N2 plus 3H2 gives rise to 2NH3. N2 plus 3H2 gives rise to 2NH3. All are gases. And fourth option, SO2Cl2, that is sulfonyl chloride gas at equilibrium with sulfur dioxide gas and chlorine gas. So what is the question now? Change in volume of the system does not alter the number of moles in which of the following equilibrium. Means by the means of change in volume, there is no change in number of moles. So for this reaction, for this condition, what is the condition should be? Condition should be, solution I'm writing here. For this, the condition should be delta n should be equal to 0. Then there is no alter the number of, does not change the number of moles. So for which of the following reactions delta n is equal to 0? First reaction, because 2 minus 1 plus 1, it is equal to 0. So first reaction, that is nitrogen plus oxygen gives us 2 nitrogen oxide. So answer is first option. Second option, if you see delta n is equal to 2 minus 1, it is 1. Third option, delta n is equal to minus 2. Fourth option, delta n is equal to 1. So, and change in volume of the system does not alter the number of moles in which of the following equilibrium, means delta n should be equal to 0. That's why the answer is N2 plus O2 gives us to 2NO. Next question. Question number 4. For calcium carbonate solid at equilibrium, that is with calcium oxide solid plus carbon dioxide gas. Carbon dioxide gas. Delta H is equal to plus Q, positive, at equilibrium, at equilibrium, comma, to shift equilibrium towards right, equilibrium towards right. Right means forward reaction. What do we have to do? Option 1, concentration of carbon dioxide should be increased. Should be increased. Option 2, concentration of carbon dioxide should be decreased. I'm writing with arrow mark, please try to understand. Then option C, pressure should increase. Then option D, temperature should decrease. Now, they have given all the 4 factors. So this question is very, very important as they've given all the 4 factors. So which is the right factor we have to identify. So for this, how to solve this question, I'll tell you. Now they are given calcium carbonate solid on heating uses calcium oxide plus carbon dioxide. This reaction is endothermic. Already we know. For endothermic reaction, equilibrium should shift towards right, means they are asking under what conditions equilibrium will shift towards forward direction. Towards forward direction. So first option they are given carbon dioxide should be increased. If you increase the concentration of products, the equilibrium will shift towards backward direction, because by increasing the concentration of parts, equilibrium will shift towards backward direction. So that is not the right option. Second one, by decreasing the concentration of carbon dioxide. If you decrease the concentration of carbon dioxide, automatically equilibrium will shift towards forward reaction because more number of parts will be formed. So answer is B. And let us see third option, by increasing the pressure. As for this reaction, delta N is equal to positive. By increasing the pressure, backward reaction. For this reaction, what is the value of delta N? Delta N is positive because 1 minus 0. So it is equal to 1. So high pressure favors backward reaction. And as this reaction is endothermic, low temperature favors backward reaction. So all other conditions is backward reaction. Only one condition is forward reaction. That is equilibrium will shift towards right side. That is only by decreasing the concentration of carbon dioxide gas. So like this, for each and every question, we have to discuss all the factors so that your concept will be very strong. Next, question number 5. Question number 5. For 2 moles of sulfur dioxide plus 1 mole of oxygen gas combines to form 2 moles of sulfur dioxide. All are gases. Delta H is given minus Q kilojoules. Minus Q kilojoules, it means exothermic reaction. Delta H is given minus Q kilojoules, it is exothermic reaction. As per Le-Chatelier's principle, as per Le-Chatelier's principle, as per Le-Chatelier's principle, which of the following change favors? Which of the following change favors forward reaction? Forward reaction, that is yielding more sulfur trioxide. Yielding, that is yielding means producing more sulfur trioxide is the question. Option, they have given 4, not options actually. They have given A, B, and C. First one, A, B. A, adding oxygen. B, adding, removing sulfur trioxide. Removing sulfur trioxide. This is multiple choice question. C, applying high pressure. Applying high pressure. And D, change of catalyst. Change of catalyst. Now, first option. A, B, C, and D all are correct. Second option, A, B, and D. Third option, A and D. And fourth option, A, B, and C. Fourth option, A, B, and C. These are the four options they have given. So now let us see the solution for this. By adding oxygen, first is by adding oxygen. If you add oxygen, what happens? By increasing the concentration of reactants. If you increase the concentration of reactants, equilibrium will shift in forward reaction. That is, more amount of sulfur trioxide is formed. So by increasing the concentration of reactants, because oxygen is the reactant, so by adding O2, forward reaction takes place. So first condition is correct. So A is correct. Next condition is B, by removing sulfur trioxide. If you decrease the concentration of products also, reaction will shift in forward direction. So already we know, if you, since sulfur trioxide is the product, by removing sulfur trioxide means by decreasing the concentration of product. So if you decrease the concentration of product, the reaction favors forward reaction. So B is also correct. Next, by applying high pressure, since for applying pressure, we need to check delta N values. So delta N is equal to, for this reaction, 2 minus 3, it is minus 1. So 2 minus 3, it is minus 1. If delta N is less than 0, if delta N is less than 0, high pressure favors forward reaction. High pressure favors forward reaction. So third option is also correct. That is, applying high pressure is also correct, because for delta N, if the reaction is for delta N less than 0, high pressure favors forward reaction. This we have seen already in explaining Lee-Chatter's principle. Last one, change of catalyst. So a catalyst has no effect on equilibrium. So change of catalyst does not alter. So answer is A, B, and C. That is fourth option. So like this, we have to discuss all the points. So answer is fourth option, A, B, and C. So this is the answer. By adding O2, we can increase sulfur trioxide, production of sulfur trioxide. By removing sulfur trioxide also, we can increase the sulfur trioxide production, because in these two cases, equilibrium will shift towards right side, that is forward reaction takes place, because for the production of sulfur dioxide, we require forward reaction only. So third one, by applying high pressure, as delta N is less than 0 for this reaction delta N is less than 0. So high pressure favors forward reaction. High pressure favors forward reaction. So answer is A, B, and C. All the three options are correct. A, B, and C. Next question. Next, question number 6. So please note down all these questions. Question number 6. At least 10 questions I want to discuss so that you'll get perfection in topic. So next, question number 6. Kc for hydrogen plus half O2 gives rise to H2O, that is equilibrium reaction. At 500 kelvins is 2.4 in 10 to the power 47. 2.4 in 10 to the power 47. This is very typical question. Now backward reaction is favored by. Now backward reaction, that is water changing into hydrogen and oxygen. Backward reaction. Anyway, I'll write complete question. Now backward reaction is favored by. Backward reaction is favored by. Backward reaction is favored by option 1, high pressure. Option 2, high temperature. Option 3, presence of catalyst, that is platinum. Presence of platinum. And option D, addition of helium gas. Addition of helium, that is inert gas. So these are the 4 points we have. So Kc for this reaction is given simply, that is at 500 kelvins, that is 2.4 10 to the power 47. So now backward reaction is favored by. So let us see. This is water is gas. Let us consider all our gases. Even no need to consider gas also, straight away by seeing Kc value. As Kc value, since for this reaction solution, by taking Kc value only you have to consider. Since Kc is greater than 10 to the power of 3, the reaction almost completes. Reaction is completed. So to bring back to backward reaction, for this reaction, since hydrogen combines with oxygen, this is combustion reactions. All combustion reactions are exothermic in nature. So this we can say, we cannot say this is combustion. We say high temperature. So let us see now. High pressure favors forward reaction or backward reaction. High temperature, presence of catalyst. Anyway, presence of catalyst, we know it is not the right answer because change of catalyst, no need of this thing. Means there is no effect on equilibrium. Addition of helium gas. So as they have not mentioned the reaction is carried out at constant pressure and constant volume, we cannot say addition of helium gas because they have to mention here constant pressure or constant volume. Then only we can say, but they are given only constant temperature. So we cannot say about addition of here helium gas. So answer could be either high pressure or high temperature. So for this reaction, delta N is equal to 1 minus half, that is 0.5. So high pressure favors forward reaction. Now they are asking backward reaction. So as since for this reaction, what is delta N value? Delta N is equal to 1 minus 1 and half. 1 minus 1.5, it is equal to minus 0.5. Since delta N is equal to negative, we can say it is high pressure favors forward reaction. High pressure favors forward reaction, but we require backward reaction. So anyway, this is not the right answer. So answer is only high temperature. High temperature favors forward reaction, backward reaction. High temperature favors backward reaction since this is exothermic reaction. Since combustion reaction, since it is exothermic because all combustion reactions are exothermic. Exothermic reaction, high temperature favors backward reaction. High temperature favors backward reaction. So straight away answer is option 2. Next question. So please copy down that questions. Whenever I have written the questions, you also copy down. Next question number 7. Just made. Question number 7. In the equilibrium, like this, at least 20-25 questions if you do from other materials, 100% you will be master in that concept. In the equilibrium, ammonium hydrogen sulfide, that is solid, gives rise to ammonia plus hydrogen sulfide gas. Ammonia gas plus hydrogen sulfide gas. Hydrogen sulfide gas. The forward reaction can be favored by, they are asking, the forward reaction. The forward reaction can be favored by option 1, first option, by adding some more ammonium by adding some more ammonium hydrogen sulfide. Second option, by adding some more ammonia, adding some ammonia, some more ammonia gas. Third option, by removing some ammonia, by removing some ammonia from the reaction mixture, from the reaction mixture. And option 4, by adding some more hydrogen sulfide gas. This question is very, very typical. It's easy also. For confusion sake, they have given like this. So now you can see the solution for this. So in the equilibrium, ammonium hydrogen sulfide, that is solid, changes to ammonia gas and hydrogen sulfide gas. So first important condition is solid. By the addition of solid, there is no equilibrium because concentration of solid is taken as unity. There is no effect on equilibrium. So by adding some more ammonium hydrogen sulfide, actually the equilibrium will shift towards forward direction. But since this is solid, so by adding some more hydrogen sulfide, ammonium hydrogen sulfide, there is no change in equilibrium. So first option is wrong. Second, by adding some more ammonia means as the concentration of products increases, since ammonia is product, as the concentration of products increases, backward reaction takes place. What reaction? Backward reaction. So by adding some more ammonia is also wrong. And by decreasing the concentration of products, we can say forward reaction takes place. So answer is third option. By adding some more H2S means even by increasing the concentration of product because hydrogen sulfide is product. So in this ammonia, by decreasing the concentration of product, we can say forward reaction takes place. Forward reaction can be favored by removing some ammonia from the reaction mixture. We can say the equilibrium will shift towards forward direction. So this is question number 7. So please copy down. Next we'll see question number 8. Question number 8. At least 10 questions we are, as I told you, I want to discuss. So I'm discussing all these questions. Next question number 8. Lee-Chatter's principle. Lee-Chatter's principle is applicable to first option, that is A option. Option A, chemical equilibrium only. Chemical equilibrium only. Option B, physical equilibrium, means the equilibrium in physical state, physical process. Option C, both physical and chemical equilibrium. And option D, gaseous state only. Gaseous systems only. So answer is simple direct question. It is applicable for both physical and chemical equilibrium. Physical and chemical equilibrium. Example, H2O gases, H2O liquid is in equilibrium with H2O gas. So for this, we can say forward reaction by heating, backward reaction by cooling. So for this, suppose if you want to increase the forward reaction, rise of temperature shift equilibrium towards rights in case of, so as this is, since for this was delta H is positive, high temperature favors forward reaction. So it is applicable to physical equilibrium also. That is nothing but physical process which is at equilibrium. This is the example I have given. So Lee-Chatter's principle is applicable to both physical and chemical equilibria. Next question. Question number 9. Question number 9. Acetic acid. Acetic acid dissociates as CH3COOH is a formula of acetic acid, gives rise to CH3COO minus and H plus. If a little amount of sodium acetate, if a little amount of sodium acetate, that is CH3COONA, is added to its aqueous solution, is added to its aqueous solution, what happens? Option 1, the acid dissociates further. Typical question this is. Option 2, the H plus ion concentration increases. The H plus ion concentration increases. Option 3, the acid dissociation is suppressed. The acid dissociation the acid dissociation is suppressed. And fourth option, the equilibrium is unaffected. The equilibrium is unaffected. So in this case, writing the solution now. So the acid dissociates further. So if you dissolve acetic acid, so it dissociates as acetate ion plus H plus ions. If a little amount of sodium acetate, that is CH3CONA, is added to its aqueous solution, the acid dissociates further, H plus ion concentration increases, and the acid solution is suppressed, the equilibrium is unaffected. So when it happens like this, what happens here? If you add a little amount of sodium acetate, what happens? Sodium acetate also dissociates to form CH3CONA, also dissociates to form CH3COO minus and Na plus. So this CH3COO minus combines with H plus of this reaction, and again it forms acetic acid. So this is nothing but the common ion effect. This is also called, because the common ion is in both the cases, it is called acetate ion. Acetate ion is a common ion. So this will combine with H plus ion and forms acetic acid. So the acid dissociation is suppressed in this case. The acid dissociation is suppressed because due to common ion effect. Common ion effect. This common ion effect we'll discuss. So this is due to common ion effect. So here, what is the common ion? Because here in this case, CH3CO minus. When sodium acetate is added to acetic acid, for this solution, if it is added, what happens? In the acetic acid, CH3CO minus ions forms, and in sodium acetate also CH3CO minus ions is formed. This CH3CO minus combines with H plus ions in the first case and forms acetic acid again. So due to so it is forming acetic acid. So the dissociation of acetic acid is suppressed, that is stopped. So this is called common ion effect. This is called what? Common ion effect. Due to common ion effect, the acid dissociation is suppressed in this case. Due to common ion effect, the acid dissociation is suppressed in this case. So please note down in your classwork this question as well as the answer. Meanwhile, Next question, last question. Then we'll discuss summary of the topic. Next question, note down in your classwork. Question number 10. Consider the reaction. Consider the reaction consider the reaction equilibrium. Equilibrium. 2SO2 plus O2 gives rise to 2SO3 is formation of sulfur trioxide, and delta H is also given. Standard enthalpy change delta H degree is equal to minus 195 kilojoules. Minus 195 kilojoules. On the basis of Lee-Chatter's principle, on the basis of Lee-Chatter's principle, Lee-Chatter's principle, the conditions favorable, the conditions favorable for the forward reaction is for the forward reaction, that is yielding of sulfur dioxide. Forward reaction is JEE Mains question. First option A, by increasing temperature as well as pressure. By increasing temperature as well as pressure. Option B, by lowering the temperature. Till now we have got only one condition. Now they are asking two conditions. That is by lowering the temperature and increasing the pressure. That is second option. And increasing the pressure. Even they can give all the four options also for increasing the pressure. Option C, any value of temperature and pressure. Any value of temperature and pressure. And option D, lowering of by decreasing the temperature and also decreasing the pressure. That is lowering of temperature and pressure. That is the fourth option. So let us see the solution now. So for this reaction, solution, easily you can understand. Forward reaction. So first for temperature and pressure. For temperature, since this is exothermic reaction, because delta H is negative, so it is exothermic reaction. Since it is exothermic reaction, low temperature favors forward reaction. Low temperature favors forward reaction. Now, because they are given all pressure and temperature, so let us check the pressure also. Since delta N is equal to 2 minus 4, it is minus 2. 2 minus 3, it is minus 1. It is negative. Since delta N is less than 0, high pressure favors forward reaction. High pressure favors forward reaction. So these are the two conditions, that is low temperature favors forward reaction and high pressure favors forward reaction for this reaction, which is at equilibrium. So answer is by decreasing the temperature and increasing the pressure. By decreasing the temperature, by lowering the temperature and increasing the pressure. So sulfur trioxide is formed. That is forward reaction is favorable. Like these questions are most important. So practice as many questions as you can from entrance books. This very, very important concept. Now, now I'll write summary of the chapter because chemical equilibrium is completed. Summary of the chapter. Very simple topic, but most important summary of the chapter. So first we have chemical equilibrium. What is chemical equilibrium? And factors affecting equilibrium constant. Factors affecting equilibrium constant. Second, we have relation between Kp and Kc. Third, we have relation between Kc and delta G. Relation between Kc and standard free energy change. And fourth topic, we have de-Jacques principle and its application. De-Jacques principle and its application. What is the main application of de-Jacques principle? De-Jacques principle can give the best conditions for the reaction to take place. So it can give the best conditions for the reaction. So if you want a product, you can increase the conditions by increasing the temperature, pressure, volume, or concentration, because we know the factors affecting equilibrium. So de-Jacques principle can give the best conditions for the reaction to take place. Best conditions for the reaction to take place. Please note on that point. So de-Jacques principle and its application. So these are the four topics we have. So all the four topics is very, very important, because from 1 to 3 you'll get numericals. From first 2 and 3 chapters you'll get numericals, and from this topic you'll get theoretical question that is based on conditions. So all the conditions are important. So what are the conditions applying the Chatter principle? First one, we have concentration, effect of concentration. Second one, we have volume. Third one, we have effect of pressure. Fourth one, we have temperature, effect of temperature. And fifth one, we have addition of inert gas. And fifth one, we have addition of inert gas. So all these 5 factors, please note it down. What happens if they increase? What happens if they decrease? Definitely that type of questions will be coming for entrance exam. So that is, all the 4 topics are important. It's very, very small chapter, and all the 4 topics are important. We have done enough models from this chapter. So that's why all the models what we have covered in these sessions, that is 5 lectures, please follow it properly and do accordingly the questions based on this in your entrance books. So with this I'm continuing. With this I'm stopping this class. So chemical equilibrium is finished. It's very, very important topic. Thank you all.